This video is going to cover electrical potential for Special Higher Physics 1B. Electrical potential is related to the work done on moving a charge through an electric field. Remember, work is equal to the force times the distance, so dot product between them. For electromagnetism, we can write that the change in potential energy is equal to minus F dot ds as we move a particle, a positive charge, in an electric field from A to B. To write this in terms of the electric field, we can use F is equal to EQ, so we can write this as minus Q from A to B of E dot ds. Now the negative sign comes about because as the particle moves from A to B, it is losing electrical potential energy. Now the size of this integral, you would think, might depend upon the path you take. It might depend on how you go from A to B. Let's have a look and consider a few different paths between particles A and B. So we've got some electric field. Let's draw a charge down here. Here's our charge plus Q. It's got electric field lines radiating out from it like this. And now let's have our point A and point B, and we'll consider a couple of different paths between A and B. Let's first of all consider a path which goes parallel to these field lines and then along an arc of a circle centered around this charge plus Q. So now you can see this part of the field line, E dot ds, is just going to be E times the path length, as the E and the ds are parallel. Along this part, the arc, the E and the ds, this is the direction of the ds here, are always perpendicular. So this is not going to contribute to this integral here. So let's call this path 1. We can write that the change in potential energy along path 1 is equal to minus Q. And now let's call this RA, meaning the distance from A, and RB. That's at distance RB. So we've got from RA to RB of E. Now the electric field caused by a point charge is given by 1 over 4 pi epsilon naught Q. This Q refers to this Q here, setting up the electric field. This Q here is our Q naught, our test particle that is being moved from A to B. And this is over R squared dr. And then along this arc part, we've got no contribution. So this is equal to minus Q naught 1 over 4 pi epsilon naught. That Q's constant, so it's out the front. Now when we integrate 1 on R squared, we end up with minus 1 on R. And this is from RB to RA. And so this is equal to minus Q naught Q over 4 pi epsilon naught 1 on RA minus 1 on RB. So that's the change in potential energy along this path between A and B. Let's now consider another path. Let's do a path something like this. Now to estimate the size of this path, what we're going to do is we're going to break this path up into sections which run along the arc of a circle centered at Q, and parts which run along radiuses of that circle. So we have a path a bit like that. We'll call this is our RA, it's at radius A. We'll have radius A dash, radius A double dash, etc. all the way up to radius B. Okay, so let's work out delta U for this. This is path 1, and this new path is path 2. We've got the change in potential energy is minus Q naught from RA. Now, it's only these radial parts, the bits where we're travelling along a radius, that contribute. When we're going along an arc of a circle, the electric field lines and the path are at right angles, so they don't. So we'll have RA dash 1 over 4 pi epsilon naught q over r squared dr plus, well, minus q naught r a dash to ra double dash 1 over 4 pi epsilon naught q over r squared dr plus etc. all the way up to this last part here where we've got from ra, let's call it n dash, to rb 1 over 4 pi epsilon naught q over r squared dr. We've got a minus q naught out the front. Okay, so doing this, let's pull all the common factors out the front. So we've got minus q naught q over 4 pi epsilon naught. Now this first integral, it will have the limits 1 on RA minus 1 on RA dash. Now this second integral is going to have plus 1 on RA dash minus 1 on RA double dash. And then so on up to plus 1 on RA n dash minus 1 on RB. And you'll see each of these middle terms forms a pair where we have plus and minus of the same thing, so they end up cancelling out. So this equals minus q naught q over 4 pi epsilon naught 1 on RA minus 1 on RB. So we actually get the same change in energy whether we take path 1 or path 2. So this is actually showing us that the electric force is a conservative force. Doesn't matter what path we take, and if we go back to the same point, we'll end up with a total of 0 work being done. Now what we're going to do is try and use this to come up with a sensible definition of voltage. Now what we're going to choose is choose any point P naught at infinity. So P naught is at infinity. And we're still going to take a path from A to B and we'll work out E dot ds for that path, but we're going to force this path to go through P naught. So go from A to P naught, then P naught to B. So we can write, we've got A to B of E dot ds, and this is equal to going from A to P naught, E dot ds, and then from P naught to B of E dot ds. Now what we're going to do is define this as negative R potential at A. So this is minus VA, and we'll define this as our potential at B. So this tells us that VA is equal to the integral of A to P naught of E dot ds, and E for a point charge, that's 1 over 4 pi epsilon naught, and then we end up with the integral. We've got a Q out the front and we've got 1 on R squared dr, and this is going from A, which is at radius A, up to infinity. So this is equal to Q over 4 pi epsilon naught minus 1 on R from infinity to RA. So this is Q over 4 pi epsilon naught 1 on RA minus 1 on infinity, and this is clearly 0. So this is equal to Q over 4 pi epsilon naught RA. So this is our definition really of what voltage is caused at least by a single point charge. If it's not a single point charge, then we need to go back to this definition here. So you can see it doesn't have a direction, it only has a magnitude. So V is a scalar field. It's got a value at all points in space, but not a direction. So our voltage at any point P is equal to minus the integral from some reference point to P of E dot ds. This is what a voltage or a potential difference is. And our voltage is related to the potential energy by the potential change in potential energy per unit charge. So we can put the voltage is equal to the change in potential energy over Q, the charge that we're moving between our 2 points. So let's just write for E caused by point charge. Just from here, your voltage is equal to Q over 4 pi epsilon naught R, where R is distance between P, this is the voltage at P, and Q, where Q's at the charge that is causing the electric field. Okay, let's do a few examples. Okay, first of all, a battery has a specified potential difference delta V between its terminals and establishes that potential difference between conductors attached to the terminals. So here we go. We're placing a 12 volt battery between two conducting plates here. So this one's at 12 volts, this one's at 0 volts. This one here is positive, this one here is negative. So our electric field lines are going like this, and we've got a constant electric field between these two plates. So this plate, will say this is at x equals 0, and the distance between the plates is 0.3 centimeters. So this is at x is equal to 0.30 times 10 to the minus 2 meters. And our path between the plates, our ds, is going in this direction, the same direction as E. So what we're asked to do now is find the magnitude of the electric field between the plates. So what we know is that the voltage difference, which this is B, this is plate A, which is VB minus VA, is equal to minus the integral of E dot ds, and we're going from A to B. So let's just substitute everything in here. This is at 0, this is at 12. So this is 0 minus 12, which is minus 12. Now the A plate, that is located at x equals 0. The B plate is at 0.30 times 10 to the minus 2. Now E is constant. We're asked to find E, so we'll put E dot ds. Now because it's constant, we can move it out the front of the integral. So when we integrate, we can get rid of these negative signs. So we have 12, and then we've got E, which is some constant. So E times 0.30 times 10 to the minus 2 minus 0. And so E is equal to 12 over 0.30 times 10 to the minus 2. Solving that on the calculator, you end up with 4,000 volts per meter. So that tells us the size of the electric field in here. Okay, next example. A proton is released from rest, so V initial equals 0, in a uniform electric field. So here's our electric field, it's uniform. Here's our positive charge, and the size of this is 4 times 10 to the 4 volts per meter. And we said, assuming the only force acting on the proton is the electric force from the field, what is its velocity after it's travelled 50 centimeters? So here's point A, here's point B, they're 0.50 meters apart. So let's consider our voltage difference. What we'll need to consider is the change in energy in this situation. As the particle moves from A to B, it is losing potential energy, and all that energy which is being lost as potential energy is going into its kinetic energy. So we have that the change in potential energy is equal to negative the change in the kinetic energy. Okay, so now let's try and work out the change in the potential energy. The change in the potential energy over the charge is equal to the minus the integral of E dot ds, and this is going from A to B. So this is something that we can actually evaluate. Let's evaluate that now. A is at 0 and B is at the 0.5 meters. So we're going from 0 to 0.50. The size of E is equal to 4.0 times 10 to the 4 volts per meter, and that's ds. And so when we integrate that, we end up with minus 4.0 times 10 to the 4 times 0.50 minus 0. And so this is equal to minus 2.0 times 10 to the 4. And this is equal to delta U on Q, so that is equal to minus delta K, the change in kinetic energy on Q. And Q, that's the charge on the proton. So the change in the kinetic energy, a half mv squared, as it starts from rest, so it has no initial kinetic energy, is equal to 2 times 10 to the 4 times this charge, which is 1.602 times 10 to the minus 19. So now to get v squared, we just have to use that the mass of the proton is equal to 1.673 times 10 to the minus 27 kilograms. So now we can just substitute that in for the mass, solve for v squared, and we end up with a v is equal to 1.95 times 10 to the 6 meters per second. So it's going very, very fast by the end of it. Okay, another example. In this case, we have a charge, Q1, which is equal to 2.0 times 10 to the minus 6 coulombs, and it's at the origin. Now 3 meters above it, we have a second charge, a negative charge of Q2 is equal to minus 6.00 times 10 to the minus 6 coulombs. And then we have a point P 4 meters along here. And we're asked in part A to find the total electric potential due to these charges at point P, whose coordinates are 4, 0. So part A, find VP. Okay, so to do this, we can just use the rule of superpositions for potential. What we can do is work out the potential due to this charge and the potential due to this charge and add them together. And we know that the potential due to any point charge is equal to Q over 4 pi epsilon naught times the distance from that charge. So V of P is equal to, in this case the Q is 2.00 times 10 to the minus 6 over 4 pi epsilon naught times the distance, which is 4 squared. Sorry, 4. It's 4 meters distance here. And then we've got to add on this one. It's got a negative charge, so this potential has the opposite sign. So it's 6.00 times 10 to the minus 6 over 4 pi epsilon naught. Now this distance from Pythagoras, it's the square root of 3 squared plus 4 squared. And so that's equal to 5. So this is times 5. So we solve this on the calculator, and you end up with minus 6,291 volts. Now part B of this question says find the change in the potential energy of the system of the two charges plus a third charge, Q3, is equal to 3.00 times 10 to the minus 6 coulombs, as the later charge is moved from infinity to point P. Okay, so the change in potential energy is equal to QV. Now as we move this charge in from infinity to point P, we're moving it through the potential generated by these two charges here. So this Q is referring to this Q here, and this potential here is the potential set up by the other two charges. So this is equal to 3.00 times 10 to the minus 6 times minus 6,291 volts. So solving that on the calculator, we end up with minus 0.0189 joules. So we're actually losing potential energy by putting an additional positive charge here, as here the negative charge. Okay, so let's just have a think. Why do we use V? We've got electric fields already. Is this just introducing something else that just makes stuff harder? So we've got that the voltage at the point P is equal to minus the integral of E dot ds. This is the integral form. We could also write E is equal to the gradient of V. So what this means is this is E is a vector. So this is d dx of V, d dy of V, d dz of V. These are the same thing. So V is a scalar and E is a vector. And this inherently makes V much easier to deal with, as instead of having the 3 components for each of the spatial directions, we only have 1 component because it's a scalar. So 1, it's easier because it's a scalar. Also, we usually use V in the form 1 over 4 pi epsilon naught Q on R. This is the form for a point charge, a voltage caused by a point charge. If we were to look at the electric field in the x direction, say caused by a point charge, it'd be 1 over 4 pi epsilon naught x over r cubed. Much more complicated, and there's 3 of them. So V is generally much simpler to deal with. So if possible, use V. Now, having defined the electric field this way also leads us on to Maxwell's second equation. Maxwell's second equation tells us that the gradient crossed with the electric field is equal to 0. And let's just show that. Our electric field is given by the gradient of V. Now in maths there's a rule that says if you take the curl, that's this thing, of the gradient of something, you end up with 0 given that it's a nice function which is continuous, etc. But let's just show that. Let's just calculate what this is in the normal way we work out a cross product. So in the I direction, the J direction, and the K direction. We can write this as d dx, d dy, d dz. Then we've written this up here, dv, dx, dv, dy, dv, dz. So just working out what this is in the I direction, we've got this d dy, dv, dz minus d dz, dv, dy. Now the order we differentiate a continuous function in doesn't matter. So this and this are essentially the same. So this whole thing is 0. If we do it for the j direction, we end up with d dz dv dx minus d dx dv dz, which is again 0. And in the k direction, we've got d dx dv dy minus d dy dv dx. So this is equal to 0. And so we've just shown Maxwell's second law there. Okay, some more examples. An electric dipole consists of 2 charges of equal magnitude and opposite signs separated by a distance 2a. So to draw them, we've got charge plus q here, we've got charge minus q here, and they're separated by a distance 2a. So there's A, there's A. So the dipole's along the x-axis and it's centered at the origin. Here's our origin. So here's our y-axis and here's our x-axis. Part A says calculate the electric potential at point P on the y-axis. So here's point P, distance y up the y-axis. Now these are point charges, so we know that the voltage for a point charge is given by 1 over 4 pi epsilon naught q over r. And we also know that voltages obey the law of superposition. So the voltage at P is equal to the voltage due to the positive charge plus the voltage due to the negative charge. And so that's 1 over 4 pi epsilon naught. Let's take this out as a common factor as it will occur in both V plus Q and V minus Q over Q. And the distance between this charge and point P is this distance, so it's the square root of a squared plus y squared. And then we need to add in this voltage. This has charge minus Q and the distance is the same. It's square root of a squared plus y squared. And this is equal to 0 because these two cancel each other out. So our potential difference at P is 0. Part B says calculate the electric potential at point R on the positive x-axis. So here's our point R. It's a distance x along this axis. So we do this in exactly the same way, except that these are different distances now. So we'll substitute in again. Vp is equal to 1 over 4 pi epsilon naught. Now, plus q, the distance of that charge from our point is x plus a. The distance of the negative charge from our point is x minus a. So this is equal to q over 4 pi epsilon naught, pulling q out as a common factor, and then we'll have a common denominator, x plus a times x minus a, which is x squared minus a squared. Here we've got x minus a minus x minus a. This and this will cancel out, and so we end up with minus 2qa over 4 pi epsilon naught x squared minus a squared. So that's our answer to part B. Now part C says calculate V and EX at a point on the x-axis far from the dipole. So we have x is now much bigger than a. So let's look at the limit in this case. Well, we've got the term x squared minus a squared. If x is much bigger than a, then x squared is much bigger than a squared. So we can write Vp is approximately equal to minus qa over 4 pi epsilon naught x squared. So that's the limit of our electric potential. To work out Ex, we have to do dV dx, and so we need to take the derivative of this with respect to x. So this would be minus 2qa over 4 pi epsilon naught times minus 2, 1 over x cubed. And so this is equal to qa over pi epsilon naught x cubed. And that's our answer. Okay, next example. A rod of length L, so here's our rod, it's got length L, is located along the x-axis and has total charge Q. So we've got lambda is equal to Q on L. And it's got a linear charge density lambda. Find the electric potential at point P located on the y-axis, a distance a from the origin. Okay, so here's point P, it's a distance a from the origin up the y-axis. Now what we do is we consider the contribution to the electric potential of each little bit of charge dq. And dq is going to be equal to dx times lambda, where dx is the length of this, and it's a distance x from the origin. So we have dv, the incremental contribution to the electric potential at point P due to this point is equal to 1 over 4 pi epsilon naught dq, the charge here, over the distance from here, and this distance is given by the square root of x squared plus a squared. And so we can write this as 1 over 4 pi epsilon naught lambda dx over the square root of x squared plus a squared. Now what we need to do is try and get the total electric potential at P, so we'll need to sum up all the contributions. So V at P is equal to, let's pull the common factors out the front, 1 over 4 pi epsilon naught lambda, and then we've got the integral dx over the square root of x squared plus a squared. So we're summing up all these little dx contributions, and we're summing them from x equals 0 up to the end of the rod, which is x equals L. So we go from 0 to L. So this is 1 over 4 pi epsilon naught lambda, and then this is a standard integral. It's equal to ln of x plus the square root of a squared plus x squared, and that's at 0 and L. So we've got lambda over 4 pi epsilon naught ln, and then this is L plus the square root of a squared plus L squared minus ln of 0 plus the square root of a squared plus 0 squared, which is a. So we can write this as lambda, which is Q on L, So this is Q over 4 pi epsilon naught L log L plus A squared plus L squared. Take the square root of that all over A. And that's our final answer there for this one. Okay, and one final example for electric potential. Two perfect spherical conductors of radii R1 and R2. So here's R1, here's R2, are separated by a distance much greater than the radius of either sphere. The spheres are connected by a conducting wire. So here's our conducting wire. The charges on the spheres are Q1 and Q2. Find the ratio of the magnitudes of the electric fields at the surface of the two spheres. Okay, so what we need to do is find E1 over E2. But what we can use is the fact that these are connected by a conducting wire. Whenever you connect 2 points in a surface with a conducting wire, you force those 2 points to be at the same voltage. So there's no voltage difference between those 2 points. So the point here right on the surface must be at the same potential as the point right on this surface. And we can model these as having all the charge in the center, at least as far as the potential goes. So we can write that the voltage 1 is equal to 1 over 4 pi epsilon naught Q1 on R1, and this has to be equal to the potential at this surface, so that's 1 over 4 pi epsilon naught Q2 on R2. So this gives us, cancelling off the 1 over 4 pi epsilon naught, Q1 on R1 is equal to Q2 over R2. Now let's consider the electric field. Remember, to find the electric field we just use Gauss's law, and we'll choose a surface just outside the sphere. So there's our surface that we'll use, and then Gauss's law tells us that E dot dA is equal to the enclosed charge, which in this case is Q1 over epsilon naught. The electric field, that's what we're trying to find, and it's constant over this surface, so we can pull it out the front of the integral, and then we're integrating over the surface area. So that gives us the surface area of this sphere, which is 4 pi R1 squared, and that is equal to Q1 on epsilon naught, and this is E1, the electric field at the surface of the sphere 1. So E1 is equal to Q1 over 4 pi epsilon naught R1 squared. The expression for E2, the electric field at the surface of this sphere, can be gotten in exactly the same way. So this tells us that E1 on E2 is equal to Q1 over 4 pi epsilon naught R1 squared over Q2 over 4 pi epsilon naught R2 squared. These common factors cancel out, and we end up with Q1 R2 squared over R1 squared Q2. And now what we can do is rearrange this a bit. We can write this as Q1 on Q2 is equal to R1 on R2. So now let's substitute that in here. Replace this Q1 with Q on Q2 with R1 on R2 times R2 squared over R1 squared. And that tells us that this is equal to R2 over R1, as one of those cancels with that, and that cancels with that. Or we could write this as Q2 on Q1 if we want. Either is an acceptable way of answering this question. So that's the end of the electrical potential video.